네, ladies and gentlemen, good morning. 저는 미국 메릴랜드 대학교 물리학과 교수인 서은숙입니다. 오늘 이 스페셜 세션의 진행을 맡아보게 됐습니다. 네, 다들 어저께 즐겁고 평안한 시간을 지내셨지요? 네, 알찬 그 1일차 일정을 이제 마치고 두 번째 날 2일차 일정을 시작합니다. 네. 오늘 이제 2017년 노벨 물리학상을 수상하시고 또 현재 칼텍 캘리포니아 인스티튜트 오브 테크놀로지의 명예 교수님으로 계신 베리 씨를 모시고 기조강연을 청해 듣겠습니다. 간략하게 인적 상황을 말씀드리겠습니다. 다들 잘 아시겠지만 베리 씨는 캘리포니아의 버클리 대학에서 석사와 박사를 한 후 칼텍에서 연구원, 조교수, 부교수 그리고 교수를 거쳐서 2018년에 명예교수가 되셨습니다. 현재 미국의 National Academy of Science의 멤버시고 AAAS와 미국 물리학회 펠로우이시기도 하시며 2011년에는 미국 물리학회 회장을 역임하시기도 하셨습니다. 연구 경력은 오늘 발표하시는 내용으로 자세히 들으시겠지만은 우선 그 중력파 관측소 미국에 있는 라이고의 프로젝트 책임자시고 또 그 유럽의 그와 비슷한 이탈리아 소재의 중력파 관측소인 볼고와 라이고의 과학협력단 초대 단장을 지내셨습니다. 수상 경력도 화려하신데 노벨 물리학상뿐만 아니라 헨리 드레이퍼 메달이나 엔리코 페르미상 이런 것들을 받으셨고 무엇보다도 최근에 2023년 그러니까 불과 몇 달 전에 폴란드에서 코페르니쿠스 상을 받으셨답니다. 근데 이것은 특히 본인에게 큰 의미가 있다고 하셨는데 왜냐하면 어린 시절에 가장 처음 알게 된 과학자가 바로 코페르니쿠스라고 하셨어요. 네. 그래서 오늘 Gravitational Waves, A New Window on the Universe라는 제목으로 기조 강연을 진행해 주실 베리 씨 교수님을 큰 박수로 맞이해 주시기 바랍니다.
First, let me thank the organizers for inviting me here and back to Korea. I've been to Korea quite a few times, but not for the last few years. Today, I'm going to talk about something most of you have heard about, gravitational waves, emphasizing, because of the audience being a lot of engineers and technologists, the technical interplay between developing new technologies in order to solve problems that are needed to do breakthrough physics experiments. So that's my emphasis in this presentation. But first, I'll start with a little history. We all learned about gravity from Sir Isaac Newton. In fact, the most successful theory of physics ever is probably the theory that Newton gave in 1687 when he published a book called the Principia. And in that book, he managed to understand the basic attraction between massive bodies and gave us a formula, which I've written here. The force between two massive objects is proportional to the square of the is proportional inversely to the square of how far apart they are and the product of the masses of the two objects. Rather simple formula, multiplied by a constant that gives you the strength. It took another 100 years to understand how big that constant was. But the important point is that he called it universal gravity. And he did that because he understood more than just the problem of the apple falling from the tree or the orbit of planets, of the moon around the Earth or the Earth around the sun or the other planets. But for him, the final proof that it was universal was that he predicted the trajectory of Halley's Comet. And when he did that, then he published this book. This represents, as I said, the most successful theory of physics ever. But what one should realize is that when we use the word theory, it isn't ultimate ever in physics. It's an approximation. So all our theories are an approximation of the nature, and we learn to refine it more in time, and we get a new theory. It doesn't invalidate the earlier theory, but it means that we've moved on. So this was the first important theory of gravity, and as I said, probably the most successful theory in physics, in modern physics. However, after more than 200 years, we got a new theory of gravity brought to us by Albert Einstein in 1915. In 1905, Einstein had solved 4 of the most important problems in physics, more or less 1 month at a time, including E equals mc squared. And he spent the next 10 years trying to solve the new theory of gravity. What that meant was taking special relativity, the theory that he had that had velocities at high speed, and adding acceleration to the problem. So if he included acceleration, a simple addition in terms of parameters, it really meant learning about gravity through what he had done in 1905. It took new mathematics and a lot of complications to do that, but we got a new theory of gravity, which is much harder to understand. And generally, those of us that study physics, we teach it or take it as senior graduate students, and it's one of the most difficult courses we have to understand. It's just mathematically quite difficult. What it does is unify space and time. And it really makes us in a 4-dimensional world. We have space and time together, and they alter each other. So we have a new word called space-time. If you put it into Microsoft Word, it'll put a little wavy line under it, so it's not understood yet as a common word. But basically, that is the principle, a geometric principle that Einstein brought to us. There was only one problem physically that didn't agree exactly with Newton's theory of gravity. And that was an observation that the orbit of the planet nearest to the sun, Mercury, which has a very elliptical orbit, did not quite follow Newton's equations. As it goes around the sun, it gets moved by the position of all the present planets and moons and so forth, and you can calculate where it should come back. And by Newton's calculation by Newton's theory, it should move 532 arc seconds every century. And the observed amount was about 10% different than that. So the only discrepancy that existed when Einstein came along was about a 10% discrepancy. And in Einstein's theory, he gets the right answer for this. So we have a new theory of gravity, Einstein's theory, and it immediately explained 2 problems that existed in Newton's theory. Newton realized one of them, but not the other one. The first one was almost embarrassing when you went to school as a young kid and your teacher told you to jump up, and then you said the earth pulled you down. That was your answer why you fell down. But Newton never told us why the earth pulls us down. Why didn't you keep going up, for example? So that wasn't explained, but it is explained as soon as you look at Einstein's theory. Graphically, I've shown it here, a coordinate, more or less like a trampoline. You put a mass on it, it changes the shape. Every point on this has time as well as space. And if you put another object on it, it'll roll toward the one in the middle. And so that's why there's an attraction. It's the curvature of space-time in Einstein's theory. The second problem that was fixed, Newton actually recognized in his treatise, And that is that when the apple falls, you as an observer see the apple fall immediately in Newton's theory. There's no time that it takes for the message to come from the falling apple to you. Newton recognized that that was a problem. He called information travel at a distance, and it actually travels at a finite speed in Einstein's theory. And so if the sun, for example, were to disappear right now, we wouldn't know it for 8 minutes, because that's how long it takes at the speed of light for the message to come to us. And so likewise, gravity has a time for information to travel. And so those are conceptual. Maybe more practical, Einstein's theory of general relativity we use every day. You may not realize it, but we use it every day. And that is the GPS system. The GPS system, interestingly, is a bunch of satellites, 24 in the original setup, that are high up, and then the message goes from the person, shown in this picture, to the satellite and back to determine by triangulation basically where you are, and plot your course when you want to go from here to there. Actually, in the satellites, there's a correction. The correction is made for special relativity. That is, the satellites being so high are going about 14,000 kilometers an hour. And what we learn when we study relativity, special relativity, is that moving clock, what we learn in our head without the formula is that moving clocks, when you go fast, click more slowly. And so there's a correction, which you can calculate. And for the GPS system, it's about 7 microseconds per day. That's made in the satellites. But there's also a second correction, and that correction is for general relativity. And that comes about because the satellites are high enough that the amount of gravity is about 1/4 of what it is on the Earth's surface. And if you make that correction, it's the other sign, and it's larger. It's 45 microseconds per day. And you can put in the numbers, and if you didn't make this correction, which is made in the satellites, how long would you stay on the road? And it's only about a minute or two. So we need general relativity to do something very practical that we all do every day. So Einstein then moved on and predicted something new due to general relativity. And he did this first in a publication only a year after he published the first publication on general relativity, and that was in 1916. It's a little teeny article, only a few pages long, with mistakes in it, not very well done, and not very technical. He noticed, however, that the equations, if he looked at them a certain way, of general relativity, looked very similar to the equations of electricity and magnetism. And in electricity and magnetism, we know there's waves, electromagnetic waves, the lights in this room, radar, microwaves, so forth and so on. So he made the leap, being Einstein, that there must be waves also associated with gravity. And he wrote this in this little paper. Otherwise, the paper is quite poor and even has a mistake in it, but he wrote it. He then went on to show that how you could make gravitational waves. We recall that electromagnetic waves, when they were made, were discovered by Hertz in the late 1800s by taking two charges, moving them toward each other, going in the next room and seeing that he detected a signal, electromagnetic radiation, moved forward and backwards and saw it was wave-like. You'd like to do that again for gravitational waves. The kind of source, however, is different. It's not a dipole, it's what we call a quadrupole. And Einstein showed that in his 1918 paper. So that set us up, basically, to look for gravitational waves. What are they? They basically are a ripple in space and time created by a movement or acceleration of masses, and we look for that. If we try to do it in the laboratory, we can't make a source that's strong enough. So we've reverted to using nature to give us a source that's strong enough. And in our case, I'll show you that what that source was the merger of two what we call black holes. The size, and that's because the size is so small that we need a really strong source with present-day technology, which is pretty good technology, but it's present day. The amplitude that I'm going to talk about measuring is a very, very tiny number. It's 10 to the minus 21. So just imagine all the zeros and a 1. That's basically how much a circle, if I had a circle like this and had free masses on it, it would get distorted if a signal came from the merger of two black holes. And so that was our target, and an attempt to measure. That's several orders of magnitude smaller than the size of a proton at the level that we're at. So this is a precision measurement at a level never tried by anybody or achieved by anybody before. What the gravitational wave will do is make the circle an ellipse. And then with the frequency of the gravitational wave, the ellipse will change from being vertical to being horizontal. But the size that it changes is exaggerated in my picture here. It's only 10 to the minus 21 meters if I had a circle that was 1 meter. So the first thing we did is make the circle a lot bigger than 1 meter. Our detectors, when you see a picture, are 4 kilometers on a side. That made the problem easier by 3 orders of magnitude and moved us to 10 to the minus 18 meters, which is still much smaller than the size of a proton. This is a picture of the detectors. They're 2 interferometers, exactly identical in every respect. If we change a circuit in one, in an evening, it gets changed in the other one by morning. So they're the same. They're in physically very different environments. One in Livingston, Louisiana, a swampy pine forest, and the other in Hanford, Washington, on Department of Energy reservation, and that's high desert. It doesn't matter, that's a physical environment, they work exactly alike. So the picture on the map shows where they are. They're 3,000 kilometers apart, which means at the speed of light, if a signal were to go through one of them and go point to the other, it would take 10 milliseconds to get there, and going the other way, 10 milliseconds. So we expect that wherever the signal comes from, it'll be confined to being seen in both detectors within 10 milliseconds of each other. And I'll show you that in the data. So this is what we look for. Basically, this is what an interferometer does. It takes, I've just assumed here I had something like a couple times a second, an oscillation. And of course, I've exaggerated it tremendously. But we take a laser beam, shine it, a very special laser beam, hit a mirror that sends half of it vertically and half of it horizontally. If nothing is different, if it's the same length, both vertically and horizontally, the beam will travel each way, hit a mirror, come back. We invert one with respect to the other, and they'll exactly cancel. If, however, like the picture which I've exaggerated here is the real case, it'll take less time one direction than the other. They won't exactly cancel, and where I've written the word sensor, it'll sense it. This is highly exaggerated. The real effect is the following. We have I've simplified it to 2 major challenges that took us 20 years to get good enough to solve. One is that we have to do, people have done interferometry before, but nowhere near this kind of precision. We need to do the interferometry at the precision of 1 part in 10 to the 12th of the wavelength of the light of the laser. So a laser is already very short, the wavelength, but we have to do the precision to 1 part in 10 to the 12th of that. Interferometers that you buy commercially or in physics labs and so forth are maybe 1 part in 10 to the 2 or 10 to the 3. And so this was 10 orders of magnitude or 9 orders of magnitude better than that. And that took us many innovations over a period of 20 or 30 years. I don't have the time or the energy this morning to tell you about that. I'll tell you the other one, which is more engineering. So the second problem that we have is that we're doing this experiment here on Earth. And although for us, this room seems very stable, the Earth is really shaking a lot. and it's shaking internally, and there's a lot of what I call noise, yet we need this interferometer to be completely stable. We need to get rid of the shaking of the Earth, again, to 1 part in 10 to the 12th. That is not an easy problem, but we solved it basically with a rather simple technology, which I'll tell you about. This is just indicating that the interferometry, which I won't talk about today, had to be made from a very simple interferometer that I show up in the upper left, and like my picture, to something that's highly complex, developing enough sophistication to be able to do 1 part in 10 to the 12th of the wavelength of the light that we use. That I'll skip for now, and instead I'll talk about the engineering problem, one of the engineering problems, that is how to isolate this big interferometer from the ground to 1 part in 10 to the 12th. That we did by borrowing 2 very simple pieces of technology. The first is one that's in your car, that is shock absorbers. So a shock absorber in your car is to keep you from feeling the bump when you go over a bump on the road, and the bump would make you bump quickly up and down, and the shock absorber, which adjusts that, can't get rid of the energy that the bump gives you, but it transfers it from high energy, where it feels like a bump, high frequency, where it feels like a bump, to very low frequency, where you smoothly go over the bump. So we basically borrowed that technology and made shock absorbers for our interferometer to isolate us from the Earth. In fact, we made the world's best shock absorbers. The shock absorbers themselves are very fancy and just the right gooiness to take the problem of moving it out of our frequency band, the same thing. And we have 4 layers of it. In your car, you have 1 shock absorber. We have 4 layers of it. In fact, the shock absorbers got us a big gain, but not what we needed. It got us to 10 to the 10th. We reduced the noise or shaking of the Earth to 1 part in 10 to the 10th. We solved the rest of the problem by borrowing the idea of another technology. And that technology is one that you're familiar with if you fly in an airplane and you want to put on these little earphones that get rid of the ambient noise in the airplane. And what that's doing is measuring the ambient noise from the engines and basically canceling it. And so when you sit, you don't hear the roar of the engines, but the stewardess that comes up and asks you if you want coffee, tea, or milk, you hear perfectly clearly because she's not giving ambient noise. So we borrowed that same idea, only our problem's a little bit harder. And that is, what we did is put seismometers buried inside this array of shock absorbers and measured the residual motion caused by the shaking of the Earth, and made little actuators that push back against it. So we basically corrected actively for the motion, residual motion of the Earth, and that got us to 10 to the 12th. That was the final technical solution that got us so we can make the discovery. This is the discovery. You'll see on the left that if you can read it, this is called the strain, that's what we measure, is in units of 10 to the minus 21, just what I gave you at the beginning. And the peaks on this go up to about 10 to the minus 21 or smaller. And on the bottom scale, it's basically 0.2 of a second across. And what you're seeing is a time evolution of the signal in the interferometer. And it has little wiggles. And you can see that the top one, which is in Hanford, Washington, and the middle one, which is in Livingston, Louisiana, to the eye look pretty much alike. And in fact, if you put them on top of each other and move them just a little bit for the difference in time, when the signals arrive, they're shown in the bottom one. In fact, just to emphasize that, I show it again here, where the top one is left and right are the 2 interferometers. The next pane is interesting because it's the calculations of Einstein's equations for 2 black holes merging. And to the eye, except for it being not shaky because it's not an instrument with noise, it looks alike. The third pane, for me, the day we made this observation was the most important one. And it's what an experimentalist would look at to see if there's residual effects that you don't know about. So if I took Einstein's calculations, subtracted them from the data, I get left with this in the third pane. And you see that it's just random noise. There's no indication of any pattern in that noise. And that, as an experimentalist, is what made me have serious feelings that we had actually detected gravitational waves from the very, very beginning, just looking at that plot. So what we have is a merger of two objects. We know from Einstein's equations what they'll look like if it was two black holes. The black holes are going around each other, emitting energy in the form of gravitational waves, and slowly inspiraling until they collide and merge. The two, by calculation of Einstein's equations, are 36 times the mass of our sun and 29 times the mass of our sun. Adding that up, it's 65 times the mass of our sun. So a very heavy object compared to the size of our sun. But the final object is only 62 times the mass of our sun. And what that tells you is that equivalent of 3 solar masses of energy were emitted and went away in the form of gravitational waves. That's a lot of energy. We have to work hard to detect it because the effect on space and time is so small. Basically, if you think of space as a material, if you're a material scientist, it's just incredibly stiff. And maybe we're lucky we live in a universe that the space is very stiff, but it's effectively very stiff. So we then calculate the parameters, as I said, and we get all the features of the black holes, and we can study those, and that's a physics problem that I won't talk about today. I want to talk about one other observation, and that is the observation of what are called neutron stars. You all know that black holes don't emit anything anybody can see. It's why we call them black holes. They emit nothing. But neutron stars are the product of the end death of a star, and basically are a heavy, compact object made out of a lot of neutrons. Is why we call them neutron stars. They actually have nuclear interactions and give signals, and we have signals, for example, we call gamma ray bursts that come from them. We saw 2 years after the initial observation in LIGO, the data that I show here on the left. On the very bottom is the gravitational wave signal. It's a time frequency plot, and it shows the time which I kept going vertically through the graphs on the top. On the top, you can see 2 different satellites that see noise and then a signal about 2 seconds after our signal. Those then were seen, and we knew that we had detected for the first time both a gravitational wave signal and electromagnetic signal, and that was tracked through every kind of frequency that telescopes use and was followed. I'll point out in this that the difference in time between our signal and the neutron star signal is 2 seconds. There should be some difference because we're measuring the dynamics of the merger, and the electromagnetic signal is the nuclear physics after it's merged. But the fact that they're within 2 seconds of each other, we identified where this object was, and it's 150 million light years away. 150 million light years is 1.5 10 to the 15 seconds. So this means that the speed of light and the speed of gravitational waves are the same to 1 part in 10 to the 15, just from this simple observation. Anyway, something else came out of this, and it shows a little bit as an example that the physics you're studying may not be the only physics that you learn when you do something new. In this case, what we realized is that the picture that we have of the merger of 2 neutron stars has very interesting nuclear physics in it. And in fact, that nuclear physics probably explains, we don't know, and the reason I use probably is we only have one observation so far, probably resolves a very old problem. And the problem is the following, that the Earth was made a long time ago, and in the Earth, if we go into the Earth, so now I'm doing geology instead of physics, in the Earth we have elements that go all the way up to very heavy ones, like uranium, for example. But the knowledge that we have of how we made elements in the universe was first mostly the universe is made out of hydrogen and helium. That's very light. And then the way stars burn is called the fusion process. The fusion process actually starts with light elements and burns to heavier ones, but when it gets to iron, it's done. So you can't make anything heavier than iron except by some exotic process. And so we never knew quite how we made things that we love so much, like gold and platinum. And now we probably have the solution to that, because if you take just a given model for how this worked, that particular collision that we saw of two neutron stars made about 100 Earth masses of gold. So that's a lot of gold. Of course, they're not the ones that got into the Earth, but presumably a neutron star merger a long time ago. So we're moving on. The experiment that we do is not limited by physics. This is another observation. We're limited by technology. So we can keep improving and making better and better instruments. When we're limited by physics background, you can't do much better except getting a lot of data. So we're doing a lot of work, and we were slowed down by the pandemic, but you can see the pictures that I don't have time to explain, making better and better interferometry, better isolation, and solving some other issues. What's shown on the right is the integral number of observations we've made of gravitational waves, starting at the bottom with a very low slope. Even though we worked so hard for 20 years, the rate was very low. We improved and it got steeper. The different colors are the different data runs since 2015, when we made the discovery. And so that's getting steeper, and we'll keep getting steeper as we add and improve our technologies over the next decade. Eventually, we'll need a new detector. We know already how to approach making a new detector. There's one approach being used in the US, which is to make basically an even bigger version of what we've made, maybe as long as 40 kilometers on an arm. And in Europe, they're looking at making it deep underground and actually making it triangular in shape. So I'm just showing this to show there's new ideas to make better detectors, as there always was with telescopes. And so opening this up as a new field of science will happen as the technology develops. The observations that we make can vary from studying, for example, the physics of the very early universe to very astronomical or cosmological questions, like what happened in the very early universe to make that when these black holes were made. I'm not going to show this because of time, but we have new features that we'll put in the interferometry, and some of the features involve quantum mechanics, and we use features, for example, called squeezed light already, where we're publishing articles not just on gravitational waves, but on quantum effects on massive objects. Once you're studying these kind of things, the effects are far beyond just the data we're using. This is just the big test mass that we'll use in the new detectors and the huge vacuum system which we're designing and doing prototype work at CERN on how to build it. One thing that we can do, just as one example, is in conjunction with the kind of physics done on the Large Hadron Collider, the physics done in heavy ion collisions, and ours is to simulate the whole space of what the early universe looked like at very high temperatures at very early times. It's difficult to probe the early universe, and we have many questions about it, and this general approach is probably the place where we'll get the most information as we move to the future. And with that, I'll quit. Thank you.
Thank you. Thank you for a fascinating talk. 네, 큰 박수 부탁드리겠습니다. 질문을 하시고 싶은 분들이 많으시리라고 예상은 되는데 시간상 그냥 넘어가야 되는 상황이 되었습니다. 그래서 개인적으로 질문을 해주시기 바랍니다. We run out of time, so we cannot take questions. We are going to take privately.